building bridges with GSA. As I said, we're going to be running through modelling of bridges, loading using influence lines, bridge loading optimization, enveloping. We're also going to look at buckling and footfall analysis options, obviously ultimate and serviceability limit states, and then a few case studies of examples where GSA has been used for some quite spectacular and indeed award-winning bridges of late. So modelling first. It's been said that one of the differences between a bridge and a building is that buildings are complex structures but with rather simple loading, but bridges on the other hand are simple structures with complex loadings. One of the main thrusts of the GSA bridge is to try and simplify the rather complex loadings that you have to deal with when designing a bridge. Now, one of the most important things in terms of the modelling aspect is the alignment. Everything comes from this thing called alignment, which of course is from the road or the railway, and we specify it by a series of straights and curves, and you get transitions between the two and so on. So you can have constant radius curves and so on, and this does need its own grid plane. The alignment will start from the origin of the grid plane, so that's another important thing to set up, which we will demonstrate now. So if I start up GSA and create a brand new model, grab my job details, and I'm going to first of all create I want the bridge to start off by going at a 1 in 4 angle from the x-axis, and the easy way to do this to create an axis, which I'm going to start off at 0, 1 in 4, and an additional point over there just to tell it which direction the XY plane is in. And we use this create user axis, and you can see the red, green and blue arrows which shows the various different options on the axis, and this one I want, which is the x-axis going up that 1 in 4 slope. I'm going to call this axis deck. I mentioned that I now need a grid plane which is defined by this axis. So a grid plane which I'm also going to call deck, and the axis is deck, the elevation is at 0. Elementless is going to be all. If you're doing a steel bridge with plan bracing, you can choose to exclude those from this, because this grid plane is going to be used for loading the bridge grillage that we're going to make. As part of the loading, we need to specify the span direction. If you have a straight bridge, you might get away with a one-way spanning bridge. This is going to be curving a bit, so we're going to have a two-way bridge, two-way spanning on each panel. Two-way and multi-way will give you pretty much the same results, except that two-way is quicker on the analysis. Grid plane tolerance is if you've got a vertical alignment on the bridge. Our bridge is going to be flat, and so we can get away with quite a small tolerance. If you had a vertical curve, then you need to set this grid plane tolerance to be quite a bit larger to make sure that everything gets included. So let's make use of this bridge. Let me just get rid of those nodes, I don't need them now. And I am going to define my current grid, which is going to be this deck. Now I also, currently these are 1 meter centers, these squares. Let me just bring that command back up again, and I'm going to change the grid layout. So I'm actually doing 1.5 meter centers, because it's going to make it easier for me to sketch on my initial part of the structure. But before we do this, let's set up the alignment. So in the bridge section, which you should see, we have the alignment, and put that down there. And then this alignment, I'm going to start with change 0, which is the origin point, and we basically said left, right, or curves or straight. So I'm going to go right curve with a radius of 50 meters. on my deck grid plane, and then change it to 25, also a right curve, also 50-meter radius. Let's switch that on so we can see what's going on. So there we have a constant radius curve. Then at 50-meter radius, I'm going to transition into a left curve with a 100-meter radius. You can see that's transitioning there, and then finally another left curve at 100. And so we have circular curve 50-meter transition and a circular curve 100 meters for our alignment. I'm now going to create some members going across, and I can sketch these in using the add elements, and I'm just going to set my default to being property number 2. Now these are going to be my cross members. If I hold the control down, I can do multiple elements. So these are going to be my cross members. These are going to be my decking pieces. And if I select those, I can copy them along the alignment. Now I use the extrude command because that picks up the alignment, and I want 30 increments at 3 meters. Now if I was to include the beams as well, it would create the whole bridge, but I want to do something slightly different in that I just want to copy those cross members. I'll set my properties back to 1, because I'm then going to pick these end nodes, and this is going to create a gridage with the co-mesh. This is the truss slabs going across. We have main beams going along, and I'm going to extrude those edge beams. 30 increments 3 meters. Include beams. So I'll extrude the nodes this time. There's my edge beams, and I'm just going to select property beam 1, which is those edge beams, and I'm going to modify those so these are dummy elements. So they'll make grid panels, but that they won't have any structural strength. And I'll pick those 3 nodes, extrude those along in 30 meters, 3 increments, and there we have our basic geometry made for the bridge. Now it's on the properties, so let's set up first of all a concrete property. We do have the standard concretes in there, but I'm going to use a code-based concrete. And as we have as we now have the American codes available, I'm going to put in an American concrete code. This is the E value includes long-term and short-term options. I'll leave it short-term, and then I'm going to create some sections and just default my concrete material there. So let's say T-beams, my longitudinal ones, 3 meters wide, flange, overall depth, that is 3 meters wide, the flange, the decking thickness, or the slab, and the web thickness, and then have a slab elements which can be rectangular, depth 300, width 3000, which 3,003 meters is our grid spacing. So we should now have a nice grillage of the elements, and we can see we have the T-beams running along the bridge and the slabs running across. Wonderful. Okay. Now, to minimise torsion in these sections, I'm just going to reduce the torsional stiffness. Not eliminate it altogether, obviously, because we will get a certain amount of torsion, but reduce the torsional stiffness just puts more moment into the major axis, which is where I want it. I'm also going to now do loading, so just static loading on here. This is going to be dead loads, so all the elements. Case 1. Now I'm just going to take half the weight. Grillages normally take half the self-weight, but this is uneven sections, so this is an approximation. You need to work out a more appropriate factor. Let's give that a name as well. So let's call it dead load. So we now need supports, endpoints, but also support here, supports there, and I just modify those and pin those in position. So we have a pin bridge, structures, sections, loads. Analyze that, and let's just make sure that penny moments. Yeah. Okay, that model looks ready to go. So, bridge load optimization. One of the important things to go on the bridge loads is something called the influence lines, which basically looking at the effect of loading at a given point, and of course they're only looking at results for that given point. I mean, this influence line is obviously for a moment at this support point, and you can see this span has some effect. Loading this span has more effect. Loads over this span has a negative effect. So you can see where best to apply the loads. You could put many influence points or influence lines on a structure, but be selective. Use your engineering judgment. Otherwise, you would end up with so much excessive quantity of results that things will start to slow down. Yeah, be selective. Keep things simple, because you then need to start doing combining and enveloping these results, and be careful with the combinations. And if one combination has 5 permutations, another has 6, and you envelope these, that's 30 permutations that GSA has to work out. We have seen models with 500 million permutations. That can take, well, you might need to, if you want to analyze that, you might need to go away and make a cup of coffee or something. On the envelopes themselves, you can also put operators on. So rather than just picking up the max and min values, you can pick just the max values, the min values, but these will lose some coexistent effects. And for example, here's sum, this is C1, this is your overall envelope. This is an envelope just the maximum values. This is an envelope looking at the absolute maximum values, taking account of their sign, and there's an absolute option, there's a min option, I think there's some other options too. So you can pick and choose to see which results you're most interested in. When doing these bridge analysis, we do have a step-by-step guide in the help. We should also be we're also recording this webinar, and assuming that recording goes well, this will be available on the website shortly. There are 3 different methods for bridge loading in GSA. There's the full optimization, to which we've just added US and Australian highway loadings into that. There is the lane-by-lane optimization, which covers others other than the highway, so railway type loads and so on. And if you want absolute full control, you can place vehicles directly onto the model and say exactly where your vehicles go. can also do construction stages. So you can analyse the effects of the structure, building the bridge up section by section. Well, I won't have time to go into that today, but we will be. There is information in previous webinars on construction sequencing, and it may well be something we'll be returning to over the coming months. So let's load up this bridge. So let's take the first of all simplest option, just defining vehicles which go directly onto the bridge. And our bridge specification I'll leave as undefined for the time being. And for this, I'll go into my bridge section, and I need to define some paths first of all. So I'm going to have a lane 1, which is going to be, let me see, we have lanes and carriageways and so on, and that position is going to, so it's going to be 1 meter over to 4 meters, and then lane 2, which is also going to be a lane from 4 to 7 meters. And we can see we've now got the lanes showing on the alignment. If I just add in the labels for that as well, you can see there are our 2 lanes, including their centre lines. For the vehicles, I am going to create a lorry. The lorry, you specify axle loads and the location of where the wheels go. So change it along. So back axle, 0 meters offset from the centre line, and the wheel load on each side, and width, which is used for lane checking, but I'm just going to take it from the wheel size. Another backwards double wheels at the back, 0.84, 47.5, 47.5, and then the front wheels, which are 4.5 meters further ahead, 1 meter offset. There's a 2 meter wide vehicle with just 45 kilonewtons on these front wheels. We then need to apply this bridge. Now I'm going to create a moving bridge load, and I am going to put it onto lane 1. Vehicles or knife edge loads. Take a vehicle, starts from change 0, ends at change 90, and we're going to put it having 1 meter steps. And the vehicle, we do have a number of supplied vehicles. I'm just going to take my lorry and so this bridge load will now run along lane 1. We could also do one for lane 2 and so on, but let's now use the bridge tools to expand that bridge loading. And what this will do is it will run that load along the bridge and create a whole series of point loads in various load cases, which if we look here, we see our bridge loads, and there it is, our first case, and we can and what we do is we analyze all these, and we can see there is our vehicle, and as it moves along you get the various bending moments and obviously deflections and so on, and to get the worst overall effects we then need to do an envelope. Now I can do an automatic envelope down here, and this will do is envelope these results, and look at the answers, and you see there are our bending moments envelopes. That's just a vehicle. If you want to include the dead load, I just edit that and add in my dead load. And as it happens, the dead load is dominating. That lorry is not having much effect on that bridge, but never mind. So that's sort of the very basic option. We can do a little bit more sophisticated option now. Let me just delete those out and delete those grid loads and delete that combination case. What I'm going to do now is do a lane by lane optimization. So I'm going to keep these two lanes. I'm going to add in a railway line down the side, and this is going to be 8 meters offset. I'm just going to take the default gauge, but we're going to say that the weight is evenly distributed over the two rails. And now to set up some path loadings to use these. And so lane 1 is going to be a vehicle. Lane 2 is also going to have these vehicular loads, and on the track we then stick a railway load, and hopefully there's a nice little fence to keep the cars and the trains separated. Once we have these in position, and then you need to do an influence line analysis. This is a new analysis task. It's bridge load optimization and influence analysis, and we need to specify some influence points. Let's delete that, because the influence points we're interested in, results we're interested in. So let's say these support points here. And this is going to be node 47, and we're interested in maximum force in the Z direction. Let me change my defaults. And node 48 and node 49. Now I'm just going to take the one support line. We'd obviously need to take all of yours rather than just the one support line. Now I also want hogging moment on that line, which means I'll take the ends of these 3 beams here. So I'll do a beam effects, new effect group. So it will check the maximum hogging and maximum reaction separately. Beam 212, beam 213, 214. Now, because I use the up and down arrows, it just copies down all the remains of the blank lines. And let's change my option to look at the beam effects, and you might just be able to make out little yellow arrows on there. I also want mid-span moments, which will be on this line here. Okay, so I'll do a new effect group. Obviously the maximum hogging and maximum sagging will be separate. 230, 231, 232, and change that output. So we've got influence line there. Now we can do a bridge optimization for the influence lines. Very good. And let's look at the results. So I have influence lines which we can display on here in global results, and we see there is our influence lobe for that sagging moment, influence line for the hogging moment. Let me just boost that a bit, and also the influence lobe for that support point. Right, that looks good. What we now need to do is optimize the loadings, which take our lane loadings. And for this, I then go to the bridge and do optimize our path loadings. And this creates a whole series of static bridge loads, various UDLs and knife flows and so on at various chainages and widths and so on. And the bridge name is a code to say what that load is expected to do. For example, if we take these ones here, these are nodal influence effects for our first effect, and these will be producing maximum reactions at that point. These ones will be producing minimum reactions at that point, and likewise the beam effect, and so on. If we expand, if we could delete ones out of here, we can judge will not be important, but I'll leave them for a moment, and I'll just expand these bridge loadings. And we don't need the moving bridge loads because that's my vehicle from earlier. And this now produces, well, let's have a look, a number of vehicle and railway patch loads. If we do a static analysis on this with our default load cases, this then produces a number of moments and so on, which of course we then envelope together as before. Now I showed you doing an automatic envelope, but if we envelope these, let me see, it's A3 to A21. I'll do a new analysis. We do a new analysis which is actually an analysis envelope. Do A3 plus A4 to A, was it 31? Was it 21? And we say we want maximum reactions and the maximum shear forces and the maximum bending moments. And so what we then get from this is like our maximum and minimum bending moments at any point and so on, which we can then design. So that is the lane by lane optimization. And if you want to make it really easy, if you've got a just a highway load, delete out all those analysis tasks because we can't have more than one bridge case. And I'm going to delete those paths, and I'm just going to create I'm going to create a carriageway on here which goes from 1 over to 7. I'm going to get a footway for the pedestrians beside the road, and that's going to be at 7.2 to 8.5, and this will of course leave some reservations either side of the bridge and a slight gap in between the carriageway and the footpath. For the loading, we just go into bridge load specification and we say we're going to use a particular bridge loading code, various options, and then we just say optimize the loading for me. So it knows the carriageway, it knows the footpath, it knows what loads should go on, where the influence points are, and just automates all those steps that we were looking at earlier to work out the worst cases, which, let's see, there is our worst bending moment, minimum bending moments, and worst knife edge loads, and then we influence those again as before, but you see it's very optimized loading restraints, loading conditions. Right. So that's loading. So you can see you can be as detailed or as quick as you want for this. Other checks you can do. You can look at the actual capacity of the structure in terms of its buckling capacity, whether for individual plate girders or for through bridge trusses and so on. So what GSA buckling analysis is doing, especially the linear buckling analysis, is it's looking for the axial loads which reduce the stiffness of the structure down to 0, and that is then obviously the buckling load. Now, axial loads have a major effect. Shear loads will have a small effect, but not a significant effect usually. And note that it's linear buckling. It's assumed the structure is in equilibrium at whatever the deformed position, which means that it's not giving the actual deflection of the structure, it's merely giving the deflected shape and the buckling load. On the other hand, if we go into non-linear buckling analysis, this is a multi-step, so this gradually increases the load on the structure and then sees how the structure deforms up to buckling point. This only works with 1D elements at the moment, so for trusses and so on. Not for 2D elements, but the deflection is the real deflection for the load. If you include material plasticity in there as well, so material yielding, that can also be taken into account. So the three options, if you look at load displacement curve with a linear buckling, it's working out the load, not the displacement. There's no unique relationship. Non-linear buckling, the displacement is related to the load, and the buckling load capacity will approach the linear buckling capacity, might even reach it. And if you're using material plasticity, so material yielding, then the buckling capacity will be a lot less than the linear capacity. So let's have a look at this example. So if I go back to GSA, now rather than this bridge obviously is not one which will buckle, but I've got a plate girder that I made earlier. And what we have here is a plate girder made up of 2D elements, and we can see I've included stiffeners at the ends. We've got self-weight, and top flange additional load. And what I want to do is find out the buckling load capacity of this beam under those loads. Now, I also want to look at the effect of the stiffeners. So what I'm going to do, I'm going to use stage definition, and say I'm going to have with the stiffeners, and that's all the elements, and without stiffeners, and that's all not property area 4. Property area 4 are those purple stiffeners at the end. And then do an analysis. I'm going to say a modal buckling on the analysis stage with stiffness. Whole model and with stiffness is the same structure, but it's useful to see a bit of guidance. First mode, I'm going to take my loads, and then I'm going to analyse that. And I'm going to do a second analysis, which is no stiffness. Again, modal buckling, but without stiffness. Take these loads and analyse that. So, end results. A torch buckling with stiffness. Let me switch off my undeformed shape. And we can see we're getting a nice lateral torsional buckle on there. So stage 2 with stiffness. And if we look at without stiffness, let me switch the solids on so you might see it better. So without stiffness we are getting web buckling, and it's a load factor of 1.2, but with stiffness it's buckling at a load factor of 2.6. So the stiffness are having quite an effect on the capacity of the section. Now this is just looking at a single plate girder. You can look at whole bridges. If you look at whole bridges, you're probably looking to use 1D elements rather than such a detailed mesh, but you can pick and choose and make the analysis as detailed as you wish. Another important bridge loading is of course footfall analysis, especially for foot bridges. Now footfall, you also obviously think about the Millennium Bridge. Now we're not really looking at this. The Millennium Footbridge was a horizontal vibration phenomenon with crowd phase locking and so on, where you have to walk in step with the bridge vibration. What we're looking at in GSA is vertical footfall, and so you can walk out of step with that, and you don't get the feedback loops that Millennium Bridge experienced. Those who are not familiar with footfall, it's looking at vibration. I mean, imagine the bridge is just a simply supported beam. It will vibrate, and with various modes of frequency, frequencies that it wants to vibrate at. And if something jumps in the middle of the bridge, it will vibrate, and vibrations will eventually die out over time due to the damping in the structure. Bridges actually vibrate at a number of different modes simultaneously. I mean, this is a simple option, so you look at the first 3 modes. Arc curve bridge, it will have slightly more complex vibration modes going on. Now, apart from the frequencies, there's also a thing called the modal mass, which is important to know about. Because remember from high school physics, force equals mass times acceleration. But what we're looking for is acceleration on the bridge, acceleration that people experience on the bridge, and acceleration is force divided by mass. Now the modal mass is not what the bridge weighs, but how much of the bridge is moving for a particular vibration mode. I mean, if we see this example, big floor slab, but only this part of the floor is actually moving for this vibration mode. So the modal mass is just a fraction of the overall structure. So output is accelerations. We can also get velocities from the analysis. Accelerations are the most important aspects, and apart from acceleration values, we also something to look for what we call a response or an R value, and this is the accelerations in comparison to this baseline curve for human perception. And this line will represent a response value of 1, twice acceleration, response value of 2. Bridges, you're usually looking at 32, 64 response values as being acceptable, because people are happy with a certain amount of bounce in a bridge which they wouldn't be happy about in a building. So examples. Let's do a footfall analysis on our bridge. Now this bridge here, this is just a grillage. For footfall analysis, we really want to model the deck as well. So to save time, I've modelled this one earlier, and you see this time it's all in 2D elements. Let me just and so we then get to the more detailed vibrations on the deck. And what we need to do for this is wait a minute, excessive stiffness down there. Let me just tweak that a minute. Let me just free those nodes up. Yeah, so what we need to do is vibrate this bridge, see what frequencies it wants to vibrate at. So first of all, a new analysis, which is a dynamic modal analysis, and low frequency structures we usually need frequencies up to 15 Hz. So I'm not showing modes. If I say 20 modes, I say cut off the analysis once we reach 15. We could add in additional loads. The self weight is automatically calculated here, but I'm just going to leave it just a few people walking around the bridge and see how much it vibrates. So that's the crucial, or the critical case. And let's have a look. So dynamic summary, and we asked for 20 modes. We've actually given us 13, and we see we're just short of 15 Hz there. And if we look at these results, let's look at our displacement contours, and indeed the shape, and you can see the various mode shapes that the bridge wants to vibrate at, and especially along the outside edge. Now they all look okay, so let's now do a second analysis, which is footfall dynamic response. And excitation of self-excitation is just looking at the vibration at the point where the person is walking, and full excitation is looking at response to the bridge, or the rest of the bridge from people walking. Areas of the bridge to look at: damping, bridge damping would be a bit lower than that. We have various footfall methods, including GSA, the Arab or Concrete Centre method, the Steel Construction Institute methods, and the American Institute of Steel Construction methods. Let's go with the Arab or Concrete Centre method. If we analyse that, so that's worked, and let's look at the results. So change my load type, load case, and look at my nodal results. So initially you get nodal results such as accelerations there, which I'll just change that units to %G, which is the American preference, 0.7% G on there, or you can get velocities out of here, or the overall response factor, such as we're looking at 9 for resident, transient not a problem, 3.5. The overall worst of both cases. Now this is the nodal results, which is right for us engineers to look at. If you want to show to the client, it's much easier to take these results and smear them onto the 2D elements. So if I look at the nodal results on elements, you then get nice, easy to understand contour plot of the response values over the structure, and we see edges, not surprising, are the most crucial area. Haven't much time to go into too much detail. We will be looking at this later on in the year. So let's press on and look at some case studies of where GSA has been used to design some award-winning and rather interesting bridges. Here's one from Price and Myers, Bristol in the UK. This is a stainless steel stress skin footbridge, and for extra interest they took the stress plots from GSA and used those to work out what perforations they could get away with in the stress skin, so that they could then put lights inside the bridge, and you sort of get, at night anyway, a negative image of the stresses in the structure. It's very pretty actually. Gatwick Air Bridge, a large footbridge over a busy airport taxiway. Obviously, because it's so busy, it had to be built off-site, as it were, around the corner, and then jacked into position in an overnight operation. Again, another extreme. This is a bamboo bridge designed by the Arab office over in Los Angeles for an art exhibition. And then a footbridge over in Limerick in the Republic of Ireland. The Living Bridge, quite a very elegant suspension bridge. Road bridge. This is a road bridge over a railway. This is going for the London Olympics, under construction at the moment. Australia, the Webb Bridge in Melbourne, sort of a stress skin half pipe with additional structure over the top occasionally. Or something quite wild, the Kurilipa Bridge in Brisbane, which is a tensegrity bridge. And yes, those are actually photographs. Doesn't look quite real, does it? The Infinity Footbridge, Institute of Structural Engineers Supreme Award, a couple of years ago. Longest footbridge in the UK, 160 metres, designed by Expedition Engineers.